Well, today's video is about proving Schroeder-Bernstein theorem. Spelled theorem wrong. You'll have to excuse the lighting. It's a little green. It was the best I could work out. Um, Schro Schroeder-Bernstein theorem states that if x is a function from x to y, and if g is a function, let me change that, from y to x, so if both f of x to y and g of y to x are injective, a bijection between the sets exists. Symbolically, this is, let me make this a little more clear. If the cardinality of x is less than the cardinality of y, and the cardinality of y is less than the cardinality of x is equal to y. Um, Symbolically, it looks really easy, but actually proving it is going to be a little more difficult. So let's go on that. Start off, Schroeder-Bernstein theorem, it works for infinite sets, which is why it's such a nice theorem to have. It works with sets of infinite size. It's pretty obvious if we take two sets, x, y, a, b, c, d, e, f, g, h. I mean, if there's an injection with f and injection with g, obviously there's a bijection because, I mean, both f and g are both bijective functions. What makes this interesting is because if you have a function of infinite size, x1, x2, x3, dot, 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 and you have y1, y2, y3, dot, 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 you know, you don't have to have what am I trying to say, every element here mapped. The function like f, for example, I'll start using some different colors for this actually, just to make it a little more clear what I mean. Let's say that this is the function f. It's going to map every element of the set x to an element of the set y, but that doesn't mean every element of y is mapped to by f because they're infinite sets. So take I'll call this blue function g. What this does, if you look, you can see y2, f does not map any element to y2, g does not map any element to x2. So neither f or g are bijective. So finding a bijective function in this slosh pot of functions, it will be there, but it's not trivial, is what I'm trying to say. I hope that makes sense. If it doesn't, you can kind of just ignore it. That was me going on a rant. Rant? A tangent. Words are hard. So there's some proofs of this which deal with like intuition and they're not formal proofs. This is going to be a formal proof using only set theory. I haven't seen another video on this online, but I'm sure it exists. I'm using my proof from Springer undergraduate textbook. Uh, First off, we need to prove a few lemmas in order to prove Schroeder-Bernstein theorem. Let's start off with lemma 1. This states that if you have a set x is a set, to find the function p, such that p is from the power set of x. Weird notation, I know. Let me try and make it a little more. There we go. To the power set of x. So p is from the power set of x to the power set of x on any set x. What we're trying to prove here is that if p is a monotonic function, such that let a be a subset of b be a subset of x, then p of a is a subset of p of b is a subset of p of x. So, it's continually increasing or decreasing, you could say. I'm gonna go with increasing. As the set increases in size, so does the function on the set. So taking that, that's what we're defining p as, a monotonic increasing function. So let x be a set, P of x, let P be monotonic such that, sorry, I'm trying to like write this all out so you can read the whole thing at once. Define P as a monotonic function such that if A is a subset of B is a subset of X, P of A is a subset of P of B is a subset of P of X. Sorry, I'm taking so long to explain this. I promise I'll get into the real math soon. The lemma states that if this is true, then there exists some set Z, subset of X, such that Z is equal to P of Z. That is what we're trying to prove. Ooh, okay. The proof goes as follows. Define Z as the union of all sets A, which are subsets of X, such that uh, A is also a subset of P of A. So we're just taking the union of all subsets A, such that when you run them through the function, the function result is bigger than A. Take any let's say take any Z inside Z. This Z, for every Z, what's the symbol? There exists a set A such that Z is in A. Sorry, I'm kind of reading over my notes here. That's just because Z is a union of all sets A. And A is a subset of P of A. You can take these two facts, stir them together to get a Z is inside P of A. Because it's inside A and A is a subset, so Z is inside P of A. Whew. Now, because A is a subset of Z, okay, P of A is a subset of P of Z. That is by our hypothesis of the function P, what we've defined it to be. So if V is an element of P of A, well, look at that. Z is also an element of P of Z. Excuse me. This means for every element Z inside Z, it is also an element of P of Z. This can prove one thing. For every element of Z, it's inside P of Z. Well, that means Z is a subset of P of Z by definition of a subset. This is where it gets a little trippy, okay? We just proved Z is a subset of P of Z. Let's use the hypothesis of our P function to go P of Z is a subset of P of Z. This works out simply because P of Z, in order for us to use the P function, we have to prove that this is what am I trying to say here? A subset of X. But because the P function is from the power set of X to the power set of X, all things ran through the function are going to be a subset of X. So P of Z is a subset of X. Just want to write that down, clarify that real quick. Because P of Z is a subset of P of Z by hypothesis, P of Z is one of the sets A up here. P of Z is equal to A, or well, one set of A. This is because P of Z is a subset of X, as we just went over, and P of Z is less than P of Z. Cool stuff. That means because P of Z is A and Z is composed of A, P of Z is a subset of Z. But wait, if P of Z is a sub if Z is a if Z is a subset of P of Z and P of Z is a subset of Z, that leaves us with Z is equal to P of Z. Ba bing ba boom. That proves lemma 1. Lemma 2, we'll write it out. Lemma 2. Try to go a little faster this time too. Lemma 2 is a let x and y be sets. Now we have let f of x of y and g of y to x be injective. So f and g are injective functions on sets x and y. For a, any subset a of x, excuse me, p of a is going to be equal to x minus g, bracket, I'll go over what that means in a moment, of y minus f of a. Ooh, almost can't fit that in there. All right, again, don't worry. What this means, the little brackets instead of parentheses, we're just going to define that to mean the set of all f of a, uh, trying to think of the actual right set theory here. F brackets of A is going to be the set of f of A for all A inside A. So, if A is equal to the set of 1 and 2, then f of A, that's not f of A. No, that's f bracket of A, which is equal to f of 1 and f of 2. Because everything is a set. Everything can be represented as a set. Cool, funky stuff. What we're trying to prove here is take this function, which we've just defined. We're trying to prove that it is also monotonic. That is, for A is a subset of B is a subset of X. P of A is a subset of P of B is a subset of P of X. Funky stuff. So, let's go over the proof right now. Let me write down the function again, because I didn't do it too well the first time. P of A is equal to X over G of, X minus G, bracket Y minus F bracket A. What this means, because this is a loaded statement, okay? It's much easier. Let's draw out some diagrams. This is going to be the set X. This is going to be the set Y. Let's say we have A, B, C, D, E, F, G, H, I, J, K, L. Because each one needs the same number of elements for it to be injective. Oh, drop my cap. So it's saying take first off, take f of a. Let's define a to be the set of A, B, and C. Just half of them, just for good measure. We're going to do f of a. I'll use red marker for f. Let's say these go to I, G, and L. So this will be, red will be f of a. Take all of y minus f of a. That's going to leave us with H, J, and K. Run that through G. Let's say this gives us D, B, and F. Now we take X minus those things we just got from G of Y minus F of A. This is going to be E, C, and A. Those are the functions that we did not, these are the elements of X, which are part of P of A. So if A is ABC, P of A is equal to A, C, and E. Once again, A, C, and E, these are just the elements which weren't chosen by the function G, where G is for all the elements that weren't chosen in the function f of A. It's a lot to keep track of, I know, but it'll get easier, and you'll see why we do it for you'll see how this connects this lemma to the last lemma. Oh, so that's just what P of A means. We still need to prove that it's monotonic though. So this proof is heavily symbolic. Have basically first we need to assume that P of A is not a subset of P of B. This means that there's some element X such that it's in P of A, but not inside P of B. Knowing what our function means, P of A is equal, excuse me, to X, G, Y, F, A, let's write out. If X is not in P of B, that means it is inside this little section of the function. I'm trying to think of a word for it. But X is inside G of Y minus F of B. This is just because it's inside this, which means like it's taken out of X because it's subtracted, so it's non-P of B. This means X is equal to G of Y for some Y inside some, I guess you could say some unique Y inside Y minus F of B. The So here's where we can start getting to, this is a proof by contradiction. We're assuming X is not in P of A, so let's keep that in mind. I'm sorry, other way around. We're assuming X is inside P of A and not inside P of B. We have this, but A is a subset of B. I forgot to write that up here, but that's like one of our hypotheses. A is a subset of B, but P of A is not a subset of P of B. A is a subset of B. This implies F of A is a subset of F of B. Just because F is a function from X to Y, you could prove it, but it's kind of easy. Trivial, I might say. Ho ho ho. What I'm getting at is that F of A is a subset of F of B. So, Y, if it's in Y minus F of B, excuse me, and Y minus F of B is a subset of Y minus F of A, you can see that because everything not inside F of B is also not going to be inside F of A. That didn't make that sort of makes everything in F of A is equal to F of B. Contrapositive. If it's not in F of B, it's not in F of A. That can get you this little handy dandy function, which you use because it's a subset. That means Y is an element of Y over F of A. Let me make those little brackets. Because y is an element of y over f of a, x is for g of y, x is inside this thingamabobber, meaning x minus that's going to be minus x, meaning x is not an element of P of A. This contradicts our initial hypothesis that it was inside P of A. So if it's inside P of A and not inside P of E, it's not inside P of A. Proof by contradiction. This proves that the function P is monotonic. With those two lemmas out of the way, we can finally start on a real proof to the Schroeder-Bernstein theorem. The proof is, let's let x, y, f, and g be exactly as they were inside lemma 2. Meaning x and y are sets, f is from x to y, g is from y to x. You know this, you know this. Define the function p on p of x. Oop, I'm gonna make that look better. P of x to p of x, such that p of a for subset a of x is equal to x minus g of all the elements of y minus f of all the elements of a. Sort of a mouthful. Because p is monotonic, and we proved that for a monotonic function, from p of x to p of x, there exists some z such that z is equal to p of z. This implies the existence of z is equal to p of c for some z which is a subset of x. First two lemmas, they all boil down to prove this. Now we can define a function. Using this, let's define a function h of x. It's going to be a piecewise function. And for every x inside x, we will use f of x if x is an element of z. Kind of hard to do lowercase versus capital when I'm writing, but if, however, x is not an element of z, we're going to do g, the inverse of g, of x. Now, this makes sense because of, keep that in mind, I'm going to erase it to get a little bit more room on the board. We're going to be doing a finite example just to show why this makes sense. Of the two sets x and y, let's say they both have 8 elements in them. A, B, C, D, E, F, G, H, 1, 2, 3, 4, 5, 6, 7, 8, I, J, K, L, M, N, O, P. Assume Z is going to be A, B, C, D, E, F, and G. I'm erasing these just so the lines will go a little easier. Let's say that these are all in set Z, and they map to, for simplicity's sake, like that. Over here, onto what will be known as f of z. What's interesting about the function z, and why we did the first two lemmas, is that take these remaining 4, these remaining 4 letters in y are g of y, sorry, these just belong to the set y minus f of v. But what's cool is that g of y minus f of z has to map to these 4 elements. P cannot map to D. Why is that? That is because Z is equal to P of Z. And P of Z would be, if you remember a function P, that would be all the elements in X that weren't mapped to by G of Y of g of y minus f of z. So if P did map to D, well then D would not be inside P of Z, and Z would not equal P of Z. So that fun little fact with Z allows us to basically say these two things, there's a bijection between them, and only allow us to worry about these last remaining elements. Every element here is going to map to an element of here. That's just how it has to work because of the set Z. I'll show this symbolically. If X is not in Z, then X is an element of G of Y of minus F of Z. Ba-boom, ba-bam. We can show pretty easily that any X in here, that's just going to be equal to G of Y for some unique Y inside Y minus F of Z. Or if you want to do it a little nicer, Y, we'll call that the inverse G of X. Ba-bam. If Y is G minus 1 of X, that fits our function up here, H, I'll write it again, where it's f of X if X is in Z, and G minus 1 of X if X is not in Z. Hope you can see why that is now. F of X will map over here, so it's like an easy bijection. There's a bijection down here. The two bijections create bijection wonderland. That's it. That is the proof. That is why you can prove for any two sets, infinite or not, if they are both injective, a bijection exists between them. Hope that was informative. I'll try to show how this can be useful, sort of. Let's say you have a graph. I don't know. Let's have an in bijection. What I want to do is I want to try to show an example where they're infinite in nature, and it's not like a finite easy one. So how about we have a bijection from, call this x, this y, just like in your old algebra class. Bijection from x to y. Every element of x maps to some element of y, but not every element of y is mapped to. These down here, nothing's mapping to them. So let's have an injection from y to x. I don't know, let me do like a, pretend it's like a parabola or something. This is a injection from y to x. Actually, how about we have it asymptotically approach so that we can be sure for every y there's an x, blah, 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 blah. But you can see what I'm getting at here? The injection x to y does not contain these values, and the injection y to x doesn't contain any of these values. So, what do we do? How do we prove there's a bijection? Well, we use our theorem. It's a lot of work to actually find z, so I won't do it. But I'll show you how these two sets, because y is injection on x and x is injection on y, we can create a bijective function using this. Let's just create a function such that it passes a horizontal and vertical line test. We'll need the function, we'll call it h of x. It's going to be what I'm writing in green. They'll need to use these values of y, which weren't used over here. So we'll go boop, boop, boop. It needs to use these values of x, which weren't used over there. Boop, 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 boop. Let me try and make this look a little better. Then, let's see. Suppose it needs to use everything from here to here. Hmm. Actually trying to write this out is a little bit of a toughie. Sorry, I'm see, it goes up. It goes like this. It needs to have these values. Ba da 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 dum. Ba da 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 dum. And then let's go ba da 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 dum. So I know this kind of looks like a mess right now, but if you check, it'll pass the horizontal line test at every point. If you go, I mean the vertical line test at every point. If you go down, there's only one point on the function h of x, and if you go horizontally, still only one point. Ba ba bum, ba ba bum, ba ba bum, ba ba bum. Huzzah! You've successfully created a bijective function, passes a horizontal and vertical line test, using two injective functions which did not cover, neither of these functions were surjective. Just two injective functions that created. That's about all for the video. I know it was a long one, and I stumbled around a lot, and it maybe wasn't the most informative, but hopefully I'll get better at making these videos as time goes on. So thank you for watching. Have a nice day, and goodbye.